Hello. So this is problem 21 from chapter 2 from Cheng, Electromagnetics. So the goal for this problem is to compute the total outward flux from the surface of a unit cube in the first octant with 1/4 the origin. So what it means by first octant, if you have your three-dimensional coordinate system, there are 8 octants. And the first one is in just positive x, positive y, and positive z. So that's all that means. You can Google that if you want a little more background info. Okay, so we have it in the first octant, and we're trying to find the total outward flux from the surface. So total outward flux. So this should sound familiar. So this is our definition for the divergence theorem. The divergence theorem is equal to the net outward, or the net rate of outward flux per unit volume. So what we're really trying to find here is the outward flux from the surface. So if we see here, when we have this ds, ds is actually, it's telling us in the divergence theorem that the rate of flux through the surface enclosing a volume is equal to the flux change inside of the volume. So this first part of the problem, though, is asking us to find the rate of flux through the surface. So I set up some of this problem ahead of time just because I did this the first time and it was just very long. The video was very long, so I'm trying to make this a little less bulky. So I'm going to go through manual setup, and then I'm just going to kind of copy and paste in some of the equation setup that I already went through. Okay, so we need 2 parts. So we're given the f for this problem. So we have that from here. And the f is going to be equal to our a in this definition. And then we need to find the ds. So the ds, or differential surface, is the differential surface and then the vector normal to the surface. So for a cube, we have 6 surfaces, and we're trying to find the flux through each of them. So our approach to solving this problem is going to be to find the differential surfaces for each side of the cube, dot all of those differential surfaces with the f that we're given, and then we're going to add it all together. So we're going to basically have the sum of the force dotted with every differential ds. So we will have ds 1 through 6 is going to be equal to our total flux. Okay. So how do we set up those differential surfaces? Okay, so let's look at them one by one here. So for our top, let's look at just this first side, differential surface for z hat. So we're going to notice that for all of the sides, we're going to use the labels with the vector directions. So we're going to have a differential surface at z hat. We're going to have a differential surface at negative z hat, because these are the vectors normal to, so perpendicular to the surface, coming out of the volume. So then we're going to have another one here at positive y hat, one here at negative y hat. And these surfaces are just the surfaces of all of the sides of the cube. One here at positive x hat, and then one, excuse the drawing, it's a little hard to kind of do behind here, but one here at negative x hat. Okay, so let's look at how we would do the ds for the z, positive z first. So ds for positive z is going to be equal to our, okay, we're doing this side here, so this side would be dx, so the change in x, because this, we notice, is our x direction, right? So we have dx for one side, because it's a differential surface, and then we have dy on this side. So dx dy in the z hat direction. Cool. Okay, let's look at ds for the negative z. So looking at the negative z, so that would be the bottom over here, we're going to have a change in y going along this side, right, from here to here, dy. So should look the same, dy, and we also have a dx. So basically the same, right? So dx, dy, except for in the negative z hat coming out of the bottom. So let's look at ds for positive y. So ds for positive y, let's erase these just so we can kind of see what side we're working with so we don't confuse ourselves. So for the positive y, we're looking at this side. And to set that guy up, we have our vertical change here, because this is one of our sides, right? This is another one of our sides. You could look at it either way. It's going to end up being the same. So dz, change in height, right? And then our change in width is going to be dx. So we'll have dx dz in the y hat, because y hat is our normal vector, and this ds is a vector value. ds in the negative y, we'll notice that this is going to be the same, dx dz, right? Just in the negative y hat. For our ds for z hat, let's look at that guy. So we can just say here, right, just to confirm, right, dx, right, change in x, dz, change in z for the negative y hat. Okay. Then for our x's, let's go ahead and look at those guys. Oops, erasing a little too much there, huh? Okay, so then let's look at our z sides. Let me get a different color, I guess. So for our positive z side, we're looking at our change this way. What is our change this way? We have dy, right, because this is moving in the y direction. And then we have dx, because this one is moving in the x direction. So we have dy dx in the z hat, and then ds in the negative z is going to be dy dx in the negative z hat. And this is multiplied by negative z. So that would be down here. Okay. Just to confirm, right, we have the same change in y on this side and the same change in x on this side. Okay. So got our setup here. So hopefully that part makes sense. I think that the setup tends to be the thing that people struggle with the most. If this part was a little confusing to you, please feel free to rewind and go back and just kind of make sure that the setup for those differential surfaces is at least partially clear. As you go on, hopefully this is a little more illuminating. So we have all of our ds values here. So what we want to do is we want to dot them all with our f vector and then evaluate them. So I put them out here. These are just the same. So this is going to be our like z and negative z that we saw up here. This is going to be our y and negative y that we saw up here, and our x and negative x that we saw up here. Oh, did I do z twice? Okay. I did do z twice, didn't I? Confused myself. Okay, let me just show you real quick. So x and negative x. And hopefully you're 2 steps ahead of me at this point and can guess what that is supposed to be. So for our x on the front face here, we have a change in y on this side and a change in z on this side. Okay, so for x coming out of the positive way, so we have dy dz in the x hat, and then we'll have dy dz in the negative x hat. And if you go ahead, we can go take a look, we can confirm that. So for that back surface there, as it's coming out here, as our negative x hat, we can confirm that that is true. We do have dy, this change here, and we do have dz, this change here. Okay, so that's our setup. And we previously set up these pieces. So our goal is going to be to evaluate all 6 of these pieces and then add them together. So let's go ahead and do that. Okay, so these are the same. This is just pre-solved out for the sake of time. Okay, so we're gonna go ahead and do 1 through 6. Okay, so starting with piece number 1 for our positive z hat side. So for piece number 1, we have f dot the ds that we found, right? and that's going to, we just copy pasted f into this first part here. So it's just copy pasting f in and then dotting it here. So an important thing to note for the unit vectors, so we have x, y, and z, and we're going to be dotting them with that ds vector in the z hat direction. That means that a lot of our terms are going to cancel. And the reason why they're canceling is because when we have two vectors that are perpendicular, they're unit vectors in this case, if you dot two perpendicular vectors, your answer is going to be 0. So x is perpendicular with z, and y is perpendicular with z. So when we dot those together, we get 0. When you dot a vector with itself, it's the magnitude of that vector squared, which in this case is 1 for unit vectors. Okay, so what does that mean for our problem? So xy, x hat, dot dx dy in the z hat. That term is going to cancel. Then we're going to have plus yz, y hat direction, dot dx dy in the z hat direction. This term also cancels because of this property over here. Then we're going to have zx z hat, dx dy in the z hat. And this term, the z hat, dot z hat is going to go to 1. So we're going to go ahead and simplify our integral and see what it looks like. So simplified, we have zx dot dx dy times 1. Okay, so next step, we need to find our bounds. So let's go back and look at that figure. So when we have a differential here, we care about those bounds, right? So we're going to take out our z. Our z is going to be a constant for this. And we want the bounds for dx, and then we want the bounds, there's x dx here. And then we want the bounds for dy. So what's the range of our x and what's the range of our y for the side that's in the positive z hat direction, right? Okay, so let's clean this up a little bit here, and let's look at the side that we care about. So the side that we care about is in the positive z, which means it's the one that's going up, right? So this is the one that we care about right here on the top. And if we look at our range for y, we go from 0 to 1 for y this way. And then we look at our range for x, we go from 0 to 1, and this is the x side, and this is the y side, right? So 0 to 1 and 0 to 1. Okay, let's go ahead and evaluate that. So let's plug in 0 to 1 for x and 0 to 1 for y. And let's go ahead and solve our integrals. So we have z, and we have x squared over 2 from 0 to 1, and then we have y from 0 to 1. Okay, so our z is a constant here, and it is important what that value is. So when we look here, our surface is located at z equals 1, right? So that's where our surface starts, so z equals 1. So we're going to plug in 1 for z on this part of the problem. So let's go ahead and evaluate that. I'm going to erase my note on the side here, but I'll leave it later on because I'll continue to repeat that. Okay, so then we have 1 for our z, and then we're going to plug in our bounds, right? So we have 1 squared over 2 times 1 for the top part minus 1 times 0 squared over 2 times 0. So we are going to get 1/2 for this first part here. So for section 1, differential surface 1 in the z hat direction, our answer is equal to 1/2 this positive z hat. And this isn't a unit that I'm applying to the answer. This is just saying this is the surface that we're looking at. I think it's just a good way to label them. Okay, so let's look at the negative side. So really similar evaluation here. What we said before, when we have x hat dot z hat or y hat dot z hat, when they're perpendicular, when you dot them, they are 0. If you dot a vector with itself, dot z hat, we can actually pull the negative out and kind of leave it with this dx dy there. So we're just looking at it as 1. Okay, so same process here, but I'll write it out. Xy x hat dot dx dy z hat plus y z y hat dot dx, oops, dx dy z hat plus, so I'm just multiplying and distributing from this top part here, plus zx in the z hat dot dx dy z hat, negative z hat. So these pieces are going to cancel because we have these two, they'll dot with each other and become 0. And then plus these two, right? So they'll dot with each other and become 0. So we'll have this integral 0 plus 0 plus, and these two are going to become negative zx, let's take out the plus here, negative zx dx dy. Okay, so then we're going to have the integral of, we're going to pull out that z as a constant, and then we have x dx, and then dy. So now we want our bounds, right? So we're looking at the negative z hat side. So let's go back up here. Let's look at our negative side. This side, so negative z hat side. So a couple of things to pay attention to here that are really important. What is our value for z? Z equals 0 here at this plane, right? So where this surface exists, z equals 0, and it's part of the problem because it's in f and it evaluates to be part of f, so it's important for our problem here. Okay, let's look at our ranges too. Okay, so on this side, maybe I'll use the, okay, so on this side, for our dy, we're going from 0 to 1, and then on this side, for our dx, we're going from 0 to 1. Again, so very similar to up here, right? The only difference from the top and the bottom surface is that one is shifted down, so that basically like one exists at z equals 1, and one exists at z equals 0 when we evaluate them. So let's go ahead and plug that in and evaluate that. So remember we have z equals 0, and up here we had z equals 1. Okay, so let's plug that in and see what happens. And then these guys go from 0 to 1 and 0 to 1. Oop, I'm forgetting an x there, aren't I? Yep. Okay, equals z, and then x squared over 2 from 0 to 1, and then y, oops, y from 0 to 1. I'm going to take and put this just at the top up here. So just an important thing to keep in mind. It's an important note. Okay, so we evaluate this, and remember z equals 0, and it's actually going to make everything end up being 0. So 0 times 1 squared over 2 times 1 minus 0 times 0 squared over 2 times 0. So our answer for this second piece here for 4 is going to be equal to 0 for the negative z hat direction. So that negative z hat side is going to be equal to 0. And that's just because of its location in the plane and just the way that that f vector evaluates out. Okay, so now let's look at the positive y. I'll try to separate these guys a little bit just to kind of keep things a little bit more legible. Okay, if this is making sense to you and you want to skip ahead to the end, we're just going to kind of do a little bit more of the same, but if you're still a little fuzzy, bear with me and hang in there. Okay, so same thing here. So we have our ds for the y direction that we found before above, and we're dotting it with f, and we're going to do the same thing first. We're going to try to cancel out our components. So let's look here. So the only thing that's going to survive is this yz y hat, because when we do the rest of these, x, y, and z, all the perpendicular dots are going to cancel. So y, 0, y dot y equals 1, z dot y equals 0. Okay, so let's go ahead and cancel those out right away. So the only thing that we care about is yz y hat dot dx dz y hat, which is going to become yz dx dz, which we can pull out our y here. So that's going to become y, and then z, dz, and dx. So let's find our bounds for z, dz, and dx for the positive y hat side. So let's go up here and look at our positive y hat side. So I'm going to, again, try to just erase some of these things to clean up what we're looking at when we look at our positive y hat side, so we can try not to get too confused with what's going on with the figure. So just trying to keep it a little bit neater, even though it's tedious. Okay, so our positive y hat side is here. We're here. Okay, so what are we looking at for x, right? This is our x direction, 0 to 1 for x. And we also have a y direction, 0 to 1 for y. Where does this exist on our plane? What is y? What is our constant y? Okay, so here, where our surface exists, y equals 1. Okay, so we need to plug in y equals 1, and then 0 to 1 for the bounds for the rest of these guys up here. Okay, so let's go down and do that. Okay, so we're here, we're at the positive y, right? Okay, 0 to 1, 0 to 1, and our y equals 1. So you may notice that when we're evaluating these guys, the z sides evaluate the same, just because of their geometry, and the y sides and the x sides will evaluate the same. The one major difference is this multiplier here based on where the plane is for the z equals 1 and z equals 0, and in this case, it's going to be the difference for this y equals 1, and then at the bottom, that y equals 0. But we'll see that as we keep going. Okay, so we're evaluating. We have y times z squared over 2 times x, and that's 0 to 1, 0 to 1, and y equals 1. So let's go ahead and plug in our numbers and just go ahead and crunch that out. Move that, y equals 1 up here. Okay. So we crunch that part out, and we're going to end up with 1 times 1 squared over 2 times 1 minus 1 times 0 squared over 2 times 0 is equal to 1/2. Okay, so we have 1/2 for this positive y piece here. So that's for the positive y hat piece here. Just for the side. So this magnitude doesn't have a direction. It's just to tell us that that's what we got from evaluating that side. So we've got 1 here. So we've got 1/2, 0, and 1/2 so far. Okay, let's look at the negative y side now. Okay, so looking at the negative y side, let's go back up to our figure. Which one do we care about? So we're looking at the other half here. So this one is negative y right up there. Okay, so for negative y, what we care about are our bounds. So for negative y, we're going from 0 to 1, and this is in the x, and then we're going from, let's see, in our y, 0 to 1, 0 to 1 in the z direction. And then what is the value of our y in this plane? Well, in this plane, our y equals 0, right? Here, our y was equal to 1. Here, our y is equal to 0. Okay, so let's plug in those numbers that we have and go ahead and take a look at what that means for our integral. So z from 0 to 1, and our x from 0 to 1, and then our y equals 0. Okay, so we're taking a look at this guy. We're going to evaluate. We're going to notice that the similar terms cancel. Feel free to work that one out for yourself to just prove to yourself that that is true. But, okay. And then we're going to go ahead and break that up. So we have our y is on the outside. We have z dz, 0 to 1 for z, and 0 to 1 for dx. And then our y is equal to 0, which is what we found from looking at our figure, from where that surface is located along the y-axis. Okay, and then we are going to evaluate that. So we'll have y and then z squared over 2 times x, and 0 to 1, and 0 to 1. So for y equals 0, so when we solve that out, we'll have 0 times 1 squared over 2 times 1 minus 0 times 0 squared over 2 times 0. So our answer is just 0 for this part, and that's for the negative y hat side. So again, if this is clicking for you, feel free to fast forward through the rest of this, or try it on your own. Otherwise, feel free to stick with me. Okay, next part, we're looking at x here. So I'm going to cross out and highlight the side that we're interested in. Let's look at the x side. So our x side is just the front and back planes kind of here. I'm sure that you can see on the figure because you're probably paying more attention as I'm just looking for things to erase in the background here. Oops. Yeah. Okay. Trying to keep things legible is a struggle sometimes. Okay, so we're looking at this first positive x, so this first flat surface right here, just coming straight out. What are our bounds here? Well, okay, so let's take a look here. So x is equal to 1 here, right? And then we have a change in z up here. So from 0, z equals 0 to z equals 1. And then across this way, we have from y equals 0 to y equals 1. So let's keep that in mind when we go down and evaluate and plug stuff in. So the positive side, x equals 1. And then if we go right ahead and then look at that, the back side, that negative side that we look at a little bit later, on the negative side, we do notice that the x equals 0 over here. So just keep that in mind. Okay, so let's evaluate here. All right, so same drill. X hat dot x hat dot x hat, y hat dot x hat, right? Z hat dot x hat. And when I'm setting this up, I'm looking at this guy, and this guy dotted with that guy. So as we saw before, a lot of those terms will cancel. So this one's going to cancel, this one's going to cancel, because when you're dotting them with perpendicular vectors, the value will go to 0. So it's nice for your math because you can get rid of a lot of terms. Okay, xy, x hat dot dy, dz, x hat is going to be equal to xy, dy, dz. So let's break that guy up, and then we find our bounds. So we're going to pull out our x because that one's constant, and then we have y, dy, and then we have dz. Okay, so we saw before that z goes from 0 to 1 and y goes from 0 to 1. So here's where our z goes from 0 to 1, all right? And here is where our y goes from 0 to 1, okay? So, and here is how we know our x is equal to 1, because the surface is located at the position x equals 1. Okay, so let's go ahead and plug that in. So we have x equals 1 here for that guy. Okay, so we have 1 times y squared over 2, 0 to 1, times z from 0 to 1. And then when we evaluate that, we have 1 times 1 squared over 2 times 1 minus 1 times 0 squared over 2 times 0. So this is also equal to 1/2 in the x hat direction here. So we're going to hold on to that piece. All right, we're getting close to the end here. We're almost done. If you've hung in with me this long, I'm impressed. Okay, so same drill here where we can cancel components. So this is going to look really similar. So x hat dot x hat 1 y hat dot x hat equals 0. And these are commutative for the dot product, so you can do them both ways. The answer is just ends up to be turns into a scalar, equals 0. Okay, so the perpendicular pieces will cancel. So this piece will cancel, this piece will cancel. We're going to end up with just super similar integral. This whole process will be the exact same answer. The one difference here is that for our plane in the negative x hat, on the negative x hat side, so negative x hat side here, which is this dark blue one that we did, maybe darkish blue. So this guy here, right here, our x is equal to 0, right? X equals 0 for the surface located on this plane. On the plane that the surface is on, x is equal to 0. So that's important because we're going to plug that into our problem. So for our last piece for this x equals 0, we're going to go ahead and evaluate. So we have x times y squared over 2 times z, 0 to 1, 0 to 1, x equals 0 here. So we're going to end up with 0 times 1 squared over 2 times 1 minus 0 times 0 squared over 2 times 0 is equal to 0 for this last piece in the negative x hat direction. So there is a property where the flux leaving all sides of like a symmetrical object, depending on the vector, can sometimes cancel out to be 0. But as you can see in this problem, it really depends on the like location in the planes. So they don't it doesn't always work out that way, but there's a flux canceling property sometimes when things are symmetrical, including the vector. Okay, so our sum of everything, so we have 1/2, 0, 1/2, 0, 1/2, 0. So 1/2 plus 0 plus 1/2 plus 0 plus 1/2 plus 0 is equal to 3/2. So 3/2 is our solution for total flux going through the volume. All right, so I'm going to go ahead and pause this video, and then we're going to look at part B next.